So let's get to work right away. In the preceding lecture, we talked about Ohm's law, resistance, conductance, resistivity, rho, which is an ohm meter, and conductivity, which is sigma. Okay, it happens. There are mental blocks. Okay, so don't worry. When I used to be a kid, more often than not, I would ask my teacher, because I used to be confused from what I read from the books. I asked my teacher, and in case I don't understand one time, then my teacher, if I ask again, he will say that तुम्हारे दिमाग में भूसा भरा हुआ है. There is a straw in your brains. No. It cannot be straw. भूसा भी नहीं हो सकता. उसमें भी कार्बोहाइड्रेट होता है. It cannot be straw because there is carbohydrate in straw. So there are times when I have mental block. Hope you don't have mental blocks. So anyway, conductivity sigma, which is in Siemens per meter, just the reciprocal figure. Now let me recall that we took a regular conductor, a regular resistor made up of the same material, isotropic material, which has same properties in all directions, and which has a regular area of cross section, a constant, and of course it has the length. The length was a variable, the area of cross section could also be a variable, and then we found that the resistance is proportional to the length. In that case, in a particular case, resistance is also proportional to 1 upon area of cross section. One item, two items. So now, who helps? The principle of mathematical consistency, which I have told you before, it comes to our help, and it says that in that case, R will be proportional to L upon A. No problem. And if there is a proportionality, then there should be a constant of proportion. And the constant of proportionality is not a function of L, is not a function of A, and also is not a function of R. Okay? Then what it is a function of? It is a function of the system. When I say the system is the thing. L, A, R, they are the defined variables of the system. This is not explicitly defined. So whatever is the system. Now, I define the system in terms of the material, its temperature, etc., etc. Okay. There could be many variables, which may not be as effective as a change in the material and a change in the temperature, etc. Okay. Then what we find is, resistivity, conductivity. How am I writing? Resist and EVT. Conduct and EVT. And I told you yesterday that when we put the EVT, TVT, ET, VT, then it is always about the material. When we use ands, tans, etc., then it is about a sample or it is about a device which has been constructed out of the materials. So basically 80% of the research in the past several centuries has been of materials. This was one of them. Okay. So what I'm writing here is very important, that EVT, ETVT, ETVT does not depend upon the shape, size, etc. of the sample, geometry, etc. of the sample. No, it does not depend. So we have rho and sigma, and rho into sigma is equal to 1. They are the reciprocal of each other. Okay. Now let's write the Ohm's law in its most familiar and musical form. V is equal to R. R is the resistance. And R has been defined as, in this particular case, as rho L upon A. We are taking the help of that particular case of a regular object in which an electric current is flowing. Rho L upon A. So I can write this equation as V is equal to rho L upon A from here into I. No problem. So I can write from here V upon L is equal to rho into I upon A. Okay. I upon A. So this equation V upon L is the kind of the potential gradient, how the potential is falling, and it is minus dVdr, or in this case minus dVdl. So this is the value of the magnitude of the electric field in the system, that point. And I upon A is defined as the magnitude of something called J. J is a vector and its magnitude is equal to I upon A. Okay. This is called current density measured in ampere per meter square. And the current density is a vector quantity. So let's go for vector representation. E is equal to, from here, E is equal to rho into vector J, which means I can also write it as the current density J is equal to 1 upon rho multiplied by E, vector E. Okay. Or because 1 upon rho is equal to sigma, so I can write this as J is equal to sigma E. This is another musical. So we have one musical and the other musical, and anything musical is not non-music. So musical things, they register here, even if you have bhusa over here, or even if you don't have even bhusa. But that is an oxymoron. So sigma is equal to 1 upon rho, Simon per meter, etc. Now, look here, friends. This current is a vector or a scalar? Current is always a scalar. So the direction that we show of the current, I have shown here, that the current is entering and the current is leaving. This is not a direction, but it is just a sense which we provide them. Okay. And here I take a cross-sectional area A, which is a surface vector, and I have the A cap, and this direction or the sense is parallel to it, so that I can write that my I is equal to current density J. What is this? dot 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 A, or else you can write A dot J. Doesn't matter because it's dot product, and the value will turn out to be equal to JA cos of theta. JA cos of theta, and because theta is equal to 0, so this will turn out to be JA in case the current is coming like this, and the surface we are talking about is this surface on this side, and both of them are in the same direction. But if the current is coming like this, and my surface under consideration is tilted, then the value of theta is not equal to 0. And then in that case, the value of theta will determine as to what is the value of the current passing through that particular area vector in these. So this is, once again, I insist that you go through it, okay? Go through it again and understand as to what happens when the current is passing, what is EVT, TVT, ET, VT, and stands, etc. Okay, and how they are related to the material. They don't depend upon, it can be of any shape and size, any bit of a material will have resistivity, conductivity. So this R is proportional to L, R is proportional to 1 upon A, etc., etc. The build-up that we have made, it is just a convenience. Else every material through which a current passes, or passes not easily, has the resistivity and has the conductivity. Okay, next we establish how this law, the Ohm's law or the resistivity law, can be obtained in terms of the movement of electrons inside a conductor, which I said and which I told you, it is Avara electrons. Now we take up something which will be a little complex for you, okay? But I've already told you about the presence of an electron gas in the metals, and this is basically according to the theory of having electrons, and in the case of several conductors that we have, and good conductors, well, the number of electrons per atom is very large, and there are some electrons which are in the outermost orbit. Some of these electrons, they get detached from their original atoms, and because the electrons are very, very tiny, very small as compared to the, it's not this big, but the ions which are created, or the atoms that are there in the body of that metal, and on the average, for example, in the case of copper, at normal temperatures, the number of electrons which are free per atom of copper is 1.1. So some of the electrons, some of the copper atoms are singly ionized, and some of them are doubly ionized. Ionized means the electrons leave that atom and they go out. Of course, within the confines of the metal, they cannot get out. We have discussed that before. Okay. That's why I am not going to indulge you in those things, and now we are going to see as to how electrons drift of electrons, and origin of resistivity, conductivity, etc. How that originates. Okay. So please be with me, very attentive. Electrons suffer collisions with heavy fixed ions, but after collision emerge with the same speed. What I said? After collision emerge with the same speed, because the electrons are, the mass of the electrons is very small. They are pithy. And what we say in Urdu, kya pitti ka shorba. Okay. So they are pithies. And these pithies, they collide with like mountainous, massy ions or whatever. And I told you about the collisions, that if an object collides with another object, of massive object at rest, then that object will emerge with the same speed, because there is hardly any transfer of momentum to the big body. Okay. So that is why I have written it with capital letters. After collision emerge with the same speed, but, again there is a but, in random directions. Okay, it all depends what is the angle at which the two bodies are going to collide, etc., etc. Now, let's use our carbohydrate over here. Okay, as I told you. So overall, the average velocity must be equal to 0. As the direction is random. Random means all directions are equally preferred and they are equally existing. Okay. So the average velocity will be equal to, some are going like this, some going like this, some coming like this. So overall, the average velocity is equal to 0. Now let us consider n electrons. N electrons in a given volume of the substance, the conductor, the metal, and this n must be very, 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 very large, billions and billions. So don't worry. Let Vi be the velocity of the ith electron, Mr. ith electron. So I can say that the average velocity Vi 1 to n sigma divided by n must be equal to 0. Okay? Perfect? No problem. Now this is when no potential difference is applied. But I am writing here, let there be an electric field. So you can say that electric field does not exist within the metal, the conductor, but temporarily we can say that it does exist. So what the electric field will provide? The electric field will give rise to a force which is EE, this force, and when I divide it by m, where m is the mass of the electron and minus E is the charge on the electron, E is equal to 1.6 into 10 to the power of minus 19 coulombs, then the acceleration turns out to be equal to like this. This is the acceleration, friends. Now, consider Mr. ith electron, or you can call Miss ith electron, whatever you like. I don't want to discriminate. So consider the ith electron at a given time t. Okay. And at the same time, let's see that the time which has elapsed has been spent after last collision for Mr. ith electron is equal to t1 second. Okay. No problem. So, if vi is its velocity just after collision, its velocity at a time ti will be equal to, we are taking this capital V as our helper right now, but capital V we have been using for voltage in such a situation. So what will happen? Now we have a formula V is equal to U plus AT. Okay, and other formula S is equal to UT plus half AT square, V square is equal to U square plus 2 AS. Then the formula that we get, V is equal to U plus AT, this is VI plus E upon M, which is the acceleration, multiplied by the time Ti, for the I time T has elapsed. So I write a formula like this. So this is a very interesting situation. So average velocity. So the average velocity of all electrons at time t, let me write it as Ti. No. Okay, at time t. I'm just writing it Ti. It's not necessary else. At time t, at the time t that we are talking about, this will be equal to what? Average of this Vi. Means all the velocities are added up, not algebraically, but vectorially, and divided by the number. No problem. So I just substitute that here. One part is this and the other part is this. Okay. But this part we have already shown that is equal to 0. Okay. Now, collisions are taking place by Mr. Electron number 1, 2, 3, 4, Mr. N. They are all colliding. They are moving in all possible directions with, I will not say all possible velocities, okay, but varying velocities. So, now if we say that we take the average of the time that elapses between collisions and say that let tau, this tau, the same we use for torque, but here it's for time. Let tau be the average time between successive collisions. One collision, second collision, the third collision, and this collision, and that collision. Okay. And let us say that because of the presence of the electric field, okay, there is a drift. There is a drift of electrons. It does not mean that all electrons start moving in the same direction. No, they will still be random. But on the average, the electrons will have a drift speed, a drift velocity, okay, opposite to the electric field. Electrons are negatively charged, remember. So, I can write this. Drift velocity is equal to the average of Vi, which is equal to average of small vi plus average of this quantity, etc. Okay. So I can write this as equal to 0, average value of this is equal to 0, and this turns out to be equal to minus EE upon M into the tau. So Vd is equal to a quantity like this. Okay, your pen is not working, sir. Okay, so I return, okay, to make a few, I'll take a few more minutes for you and I'll explain as Anyway, consider that this has been put in the circuit. Okay, I can put it in the circuit. A red circuit. Red is visible. Okay, so I return and tell you more about it. So let me take a few more minutes. Vd was found to be equal to minus E upon m into tau. Okay. Now this result is surprising. It is surprising. Why? Because Vd has been found to be not a function of time. It doesn't change. Even when there is an acceleration. Okay. So this is surprising. Right? And this is explained in a certain complicated manner. So I leave that explanation to you. Okay? And let me see as to what is the net transfer of charge across any area perpendicular to E, and the area that has been taken is A. And we consider that now electrons are drifting against the electric field because they are negative charges, and this side must be positive, this side must be negative. And in the time delta t, the electrons will travel a distance delta x is equal to Vd into delta t. Okay. You can check the dimensions, etc. No problem. And this area here is perpendicular to the flow of electrons, the drift of electrons. So we are just considering the drift of electrons. So what will happen in this time delta t? All electrons in this length will cross the area. This is a simple consideration. All electrons which are contained within this volume, they will cross this. More electrons will come, no matter. But all electrons which are drifting like this, they will cross this area. They will give us an idea about the electric current. Now if n is the electron density, number of electrons per unit volume, okay, then I can write I into delta t. I into delta t, what is this? This is the charge which has crossed in time delta t. Because Q is equal to I into delta t. Okay, I is equal to delta Q upon delta t. So recall that, and we write N into Vd into delta t, that's the delta x, into the electronic charge, into the area that's there. The electronic charge is 1.6 into 10 to the power of minus 19 coulombs. So I can write this delta t will cancel with this delta t here, and I will get I is equal to NEAVD. NEAVD. So this is again a musical things. Okay, NEAVD. Like that. It goes. So that gives I divided by A is equal to, it has been defined as the current density, the magnitude of the current density. This is equal to NEVD. Okay. So the current density, the magnitude of the current density J will be equal to the mod of it, the magnitude of it. I can write it as NE into VD. VD I'll take from here. EE upon M into tau. So set it together, NE square upon M into tau into E. Okay. But we have defined and we have obtained J is equal to sigma E, where sigma is the conductivity. Okay, one of the two TVTs. So J will become equal to, from this relation I am writing again NE square upon M into tau multiplied by the magnitude of the electric field that has been generated by a potential difference. So I can write from this relation by analogy By comparison, this quantity becomes equal to sigma. So sigma is equal to NE square delta tau upon m. And so because rho is equal to 1 upon sigma, so this will become m upon NE square upon tau. Well, sigma is, because n is a constant for the given metal, for the given conductor, E of course is a constant, m, the mass of the electron, is also a constant, so this quantity is a constant. So the only variable, only thing which varies is the tau. Okay. And here rho will be proportional to 1 upon tau. You can draw those graphs, okay, like this, and the graph like this for rho versus tau. The average time, okay, between collisions. The average collision time is tau. Now friends, I can therefore calculate the drift velocity, okay, and the drift velocity, when I calculate the drift velocity as E upon m into tau, the value turns out to be very small, not even meters per second, fraction of a centimeter per second. So the electrons are traveling at a pace which we can call snail's pace. Okay. Well, that is the drift velocity. But the electrons are moving in all possible directions with all possible velocities, as we say. Therefore, there will be a velocity associated with the electrons, which we can define as VRMS. I've told you this, the RMS velocity in the case of heat, okay. The RMS velocity is at times is millions of times greater than the drift velocity. Okay. And the drift velocity is responsible for the current, and the current therefore is flowing due to this very small, tiny piddy drift velocity. Okay. But the information, look here, I'm just going to put off the lights on the board. Okay. How much time did it take? From on to off, very small time. And now it has come back in no time. Why it is that when the drift velocity is very small, then how this information is transferred when I switch on, switch off, etc. in such a short time? Hey, you must answer that, because the information travels within the wires which connect at the speed of light in those materials, whereas the drift velocity is, you can check, is very small. Okay. So the drift velocity upon m tau, and tau is the average time between collisions. Of course, we can talk about the path between collisions, okay, which we call mean free path, but I will not indulge into that, okay, at your stage, and I leave you here to make your life a bit shanti, om shanti. Okay, thank you very much for being with me. I've enjoyed.